Hello everyone, welcome to the presentation of our paper titled Energy Efficient Real-Time Myocardial Infarction Detection on Wearable Devices. I am Nafil Rashid, a computer engineering PhD student at University of California, Irvine, and the corresponding author of this paper. The work is done under the supervision of my PhD advisor, Professor Al Farouk, who is the Director of Embedded and Cyber Physical Systems Lab at University of California, Irvine. So let's start. Myocardial infarction, in short MI, is also known as heart attack. About 805,000 people in the USA suffer from it every year, and among them, 605,000 people encounter it for the first time. The rest 200,000 people encounter recurrent heart attacks, and the death rate due to recurrent heart attacks is 6 times higher than that of the first ones. Moreover, 20% of the heart attacks are silent, meaning that the victims are unaware of the damage. Additionally, the victims have a higher chance of survival if they receive treatment within 90 minutes of MI initiation. All these facts lead towards the motivation of our paper. The silent nature of MI, the higher risk associated with recurrent MI, and the importance of immediate treatment emphasize the need for real-time monitoring and detection of MI. Currently, MI patients are monitored and treated in a clinical environment with a heavy medical setup. Such a solution is not feasible for real-time and daily monitoring as the devices lack portability and consume a lot of energy. Therefore, wearable devices are the perfect solution for real-time monitoring as they do not have these drawbacks. Currently, most of the wearable device solutions follow cloud computing architecture, where the raw data from the wearable devices are offloaded to the cloud. The data is then processed and analyzed in the cloud using various machine or deep learning algorithms also known as cloud AI. The analyzed result is then fed back to the user and also to the physicians for remote monitoring. However, daily monitoring of wearable devices generate enormous amount of raw data, and offloading this raw data to the cloud has the following drawbacks. It increases energy consumption of the wearable devices due to communication. It results in increased latency, which is crucial for real-time monitoring and detection. And finally, it is also vulnerable to the breach of users' personal data. These drawbacks advocate for the adoption of edge computing architecture, where all the data is processed and analyzed on the wearable devices using various machine or deep learning algorithms also known as edge AI. The analyzed result is then offloaded to the cloud, which is in turn passed to the physicians for remote monitoring. The small form factor of the wearable devices imposes constraints on the edge AI algorithms in terms of power, performance, and area. Therefore, our goal is to propose a solution that consumes low energy, provides maximum performance, and fits within the memory constraint of the wearable device. The novel contributions of our paper are as follows. We propose a real-time MI detection methodology using a binary convolutional neural network architecture. Our methodology achieves up to 12 times energy efficiency compared to the state-of-the-art work on wearable devices. It also outperforms the state-of-the-art work on wearable devices. We validate the performance of our methodology on the well-known PTB diagnostic ECG database, and finally, the energy efficiency of our methodology is validated on real hardware. As our proposed solution is targeted for wearable devices that use single-lead ECG data, we consider the works that used single-lead for MI detection. The table shows a summary of related works. As you can see, the preprocessing steps up to segmentation for all the related works, including ours, are somewhat similar. However, as related works 7, 8, and 9 used statistical machine learning algorithms as classifiers, they extracted features from the heartbeat segments applying discrete wavelet transform up to level 4 using Daubish's 6 basis function. The feature extraction process is very expensive in terms of time and energy, making these methods unsuitable for real-time MI detection on wearable devices. To overcome the tedious process of feature engineering and extraction, authors in 10 used convolutional neural network to classify between the normal and the MI heartbeats. The benefit of using CNN is that it automatically extracts features from the data through convolution and classifies them. They used 1D deep CNN architecture with 11 layers in total. Such a large architecture is unsuitable for low power and low memory wearable devices. Considering the pros and cons of all the related works, we use a binary convolutional neural network in our paper. It overcomes the tedious feature extraction process using convolution and also has less memory requirement, as the weights of the network are represented in binary. The figure shows an overview of our proposed methodology. As you can see, the raw ECG data is passed through the pre-processing steps, which is then passed to the BCNN architecture to classify a heartbeat segment. The pre-processing steps start with the denoising of raw ECG data using a bandpass filter with cutoff frequencies 5 to 15 Hz. Then, the R-peak is detected using Pan-Tompkins algorithm. And finally, we segment the heartbeat with 651 samples, 250 samples before the R-peak and 400 samples after the R-peak. We design our BCNN with the minimum number of layers possible to maintain the low power and low memory constraint while maintaining acceptable performance for the wearable devices. Therefore, we used only one fused convolution pool block and one fully connected block, and we also used Adam optimizer with a learning rate of 0.007 and softmax cross entropy as the loss function. To further reduce the memory overhead of the temporaries in standard binarized neural networks, we adopt the technique of embedded binarized neural networks. In standard binarized neural networks, the results of the convolution are stored in memory in floating point values before passing through batch normalization, binary activation, and pooling as shown in figure A. Whereas in embedded binarized neural networks, the result of the convolution is not stored in memory, rather is directly sent to pooling followed by batch normalization and binary activation as shown in figure B. Our target wearable platform is Smartcardia wearable device or similar hardware that has ultra-low power 32-bit microcontroller with ARM Cortex-M3 processor, which has maximum clock rate of 32 MHz with 48 kilobytes of RAM and 384 kilobytes of flash. The device is equipped with a 710 mAh battery and a single-lead ECG sensor. To validate the performance of our methodology, we use data of 200 subjects from PTB Diagnostic ECG database. We perform a tenfold cross-validation for our BCNN. As shown in the table, our methodology outperforms the other state-of-the-art works 8 and 9, which are intended for wearable devices, in all three metrics. We significantly improve on the sensitivity and specificity compared to 9. Although the work 8 is a close competitor for our accuracy, it does not report sensitivity and specificity. As expected, the work 7 and 10 achieves a very high performance as they are designed for clinical setup, not for wearable devices. We evaluate the energy consumption of our BCNN using an EFM32 Leopard Gecko microcontroller, which has similar specifications as the Smartcardia device. Energy profiling is done using the Simplicity Studio software that comes with the EFM32 microcontrollers. As BCNN automatically extracts features and classifies them, we compare the energy consumption of our BCNN against the feature extraction and classification steps of other wearable device solutions 8 and 9. The table shows the energy consumption of all the wearable device solutions to classify one heartbeat segment. Our BCNN consumes 536.80 microjoule, whereas the work 8 consumes 4641.62 microjoule and the work 9 consumes 6478.64 microjoule. Thus, our BCNN achieves 8 times and 12 times energy efficiency compared to the work 8 and 9 respectively. To conclude, in this paper, we propose a real-time MI detection methodology using a binary convolutional neural network that outperforms other state-of-the-art work on wearable devices. It achieves up to 12 times energy efficiency compared to the state-of-the-art work, and to the best of our knowledge, our proposed methodology is by far the fastest and most energy efficient solution for real-time MI detection on wearable devices.